equal to each other. Okay, so up until now, we've been talking about isosceles triangles and equilateral triangles, but remember, what about scaling triangles, right? Because you can classify triangles into 3 classifications based on the measurements of their sides: equilateral, isosceles, and scaling. We've already talked about isosceles and equilateral. What about scaling? So that's what we're getting into next. So this is one theorem. It's the longest side and largest angle theorem. This states that the longest side, so we see 17, 12, 20. So 20 is our longest side. The longest side of a triangle is always opposite the largest angle. So it's opposite from this angle, which is 80, and we do see that 80 is the largest angle. Okay? And we also have sort of the opposite of this theorem, the shortest side and smallest angle theorem. This states that the shortest side, we can see that the shortest side is 12, is always opposite the smallest angle. What is the angle opposite? It's 40, and we do see 40 is the smallest angle. So these two theorems, these apply to scaling triangles and isosceles triangles. Okay? So let's get into an isosceles triangle property, and then we'll look at an example for this property. This states that if an exterior angle is double one of its remote interior angles, then it's an isosceles triangle. What does that mean? Well, let's draw it out. Remember we talked about exterior angles and where we had 6 of them for a triangle? Let's zoom in. Remember, if we continued these lines, then we would get 2 exterior angles for every vertex, okay? For now, for this situation, I wanted to just focus on these. Now, let's just focus on this part, okay? So I will erase this for now. What did we notice again? Well, the exterior angle formed a linear pair with the interior angle. What does that mean? If you add these together, you would get 180, okay? So we're going to say, well, first, we don't know what this angle is, right? So we should solve for this angle, because we know if you add these two, we'll get 180. So how can we solve for this angle? Well, we know that this is 70 and this is 70, and the sum of the triangle should be 180. So 70 plus this unknown angle right here, let's call it angle 1, equals to 180. Now we just solve for angle 1, and that should give us 40. So we know this is 40. Then we can solve for the exterior angle, right? We know that this forms a linear pair with this, which means it's supplementary and adjacent. So this exterior angle, let's call it angle 2, plus 40 should give us 180 because they are a linear pair. So we just solve for angle 2 and we get 140. So we know this exterior angle is 140 degrees. Now you can see how it applies to the property. So if an exterior angle, which is this, 140, is double one of its remote interior angles. Remember, every exterior angle has 2 remote interior angles. Remember, remote means far away, so it's not touching those angles. Here are the 2 remote interior angles. Is double one of its remote interior angles, then it's an isosceles. So this exterior angle is double one of the remote interior angles, whether it be this one or this one. And because of that, we can conclude that this triangle is an isosceles triangle, okay? Now, why is this important? This is important because we're going to look at an example. This is actually what some Greek philosopher used. He used this property to solve for a real life problem, okay? So Thales wanted to measure the distance from the ship to this castle, okay? But how would he measure that distance? Is he going to walk on the shore and then start swimming? No, that might not be the best way. So he's trying to figure out this distance. Let's put a question mark. This distance. And he can only walk up and down on the shore, okay? Well, what he used was the isosceles triangle property that we just talked about, okay? So if you measure this angle, let's say he measured it to be 70 degrees, okay? And then he walked some distance along the shore, okay? Let's say he walked 20 meters. Well, yeah, sure. Now, if you look carefully and you connect it right here, this forms an isosceles triangle where these two are the legs, the congruent sides, and this is just the base, right? And now what do you notice? These are the base angles. You just have to tilt your head a little. These are the base angles, and we know the legs are congruent. Now, how do we verify it's an isosceles triangle? Well, the exterior angle, if it is double one of the remote interior angles, then it's an isosceles triangle. Well, you can't measure this angle, so you can measure this angle from the shore. And if you measure it to be 35, if you keep walking and keep walking and keep walking until finally it's 35, then this is half the exterior angle and it's an isosceles triangle, right? Because what if he only walked this distance and then it connected this way? Well, it would probably be maybe, 50 degrees. Okay, so that's not an isosceles triangle yet because this has to be half of this. So he kept walking until the angle was finally half of this, which according to the isosceles triangle property, this would make an isosceles triangle. And since he already knew this distance by walking, then he would already know the distance to the ship because by the isosceles triangle property, and these two legs would be congruent. So that is the method they always used.